Go, section 5.2, evaluate and graph polynomial functions. How do you graph a polynomial function? That's what we're going to be working on today. Here's some vocab to review. What makes up a polynomial is a monomial or a sum of monomials, each of which is called a term of the polynomial. So for example, 2x plus 3, this is a monomial, and it's a sum. So this could be called a binomial or a polynomial. Or if you have something like this, that is a polynomial. It's made up of a sum of monomials. So that's just a review. Polynomial functions, in order for it to be called a polynomial, the exponents are positive whole numbers. Otherwise, we can't say it's a polynomial function. And the coefficients are real numbers, so no I. No imaginary numbers. Synthetic substitution is a method used to evaluate a polynomial function. We'll look at that later. And end behavior is something new. It's kind of cool. The end behavior of a graph of a function as x approaches infinity or negative infinity. Okay? So start by evaluating the function. So take just a minute to practice these few skills here and then come back and see if you did it right. Okay, so this is what you should have gotten. So take a look at that. If you didn't, check out my work and see kind of what went wrong. All right, so right now we're going to start practicing what we're focusing on here. First thing I want to do is I want to take a look at page 337 in your book. Okay, this kind of talks about the common polynomial functions that we'll be having to name. So right here, if the degree of 0, that means the highest exponent, basically there isn't an x in your function, it's a constant polynomial function. If you have like this, like a linear equation, and it's a degree of 1, because remember, on any x like that, even though we don't write the exponent, it is 1. It kind of looks like this. That's linear. A squared is quadratic. The highest degree is 3. That's a cubic function. The highest degree is 4. We call it a quartic. Anything beyond that, we call a polynomial. Also, any of these could be called polynomials as well. Even though they have specific names, they fall under the general name of a polynomial. Okay? All right, so let's go back to here. Decide whether the function is a polynomial function. Make sure it meets all of these requirements up here. If so, write it in standard form, which is decreasing exponents from left to right, and state its degree, type, and leading coefficient. And this is all stuff that we've done before, except for deciding whether it's a function. So this first one here, you can see right away that this is not a whole number exponent. So it is not a function. No. And you would say exponent is not a whole number. Okay, here, this is a polynomial. It meets all the requirements, positive whole number exponents, and the coefficients are all real numbers. However, it's not in standard form. We have to rewrite it so that the exponents are decreasing in order from left to right. So it would look like this: g of x equals negative 8x to the 5th. And then I would write this term right here, plus x to the 4th. There is no third, so the next one would be negative 4x squared plus the square root of 10. And that would be a polynomial function. It has a degree of 5, because that's my highest coefficient, or excuse me, my highest exponent, my biggest exponent, degree of 5. And in standard form, the leading coefficient is going to be the coefficient in front of this variable here. So the leading coefficient is negative 8. It is a polynomial. And we're just going to call it that because the degree is 5. If it was 2, 3, 4, we would have more specific names. Alrighty? So let's look here. This is also a polynomial. The exponents are positive whole numbers. The coefficients are real numbers. So yes. It's in standard form already, decreasing exponents. It has a degree of 3, a leading coefficient of 1, and since the degree is 3, it's cubic. Okay, take a look at this one here for a second, see if you notice whether it is a polynomial or not. And notice that this exponent is a negative 2, so that makes it not a polynomial function. Negative exponent. All right, so that's identifying whether it's a polynomial function or not. All right, next page. Use direct substitution to evaluate the equation with the given value of x. Direct substitution is basically what you've been doing your whole algebra career. All you do is if they give you the value for x, you substitute it in wherever x is. So I'm going to say f of 2. That means 2 is going into my function. Anywhere there's an x. And when the fishy swallows a 2, those of my students that had me know what I'm talking about. Let's see what the value is that comes out. Basically, this is the input. It equals the output when we do the math. So f of 2 equals negative 49 when I do that math on the calculator. This is what went in. This is what came out of the function. All right, and let's do the same thing here with negative 2. Again, you want to be careful when you're doing a negative raised to an exponent on the calculator. You want to make sure you put it in parentheses because the calculator is smart and it follows order of operations, and if you don't have it in parentheses, it won't read it correctly. So again, this is the fishy swallowing a negative 2. Let's see what it poops out here. So to evaluate this function, when the input is negative 2, the output will be 5. And that's using direct substitution, just plugging it in wherever there's an x. Now we're going to learn a new way to evaluate. Okay, it's called synthetic substitution. It's pretty cool, actually. I haven't used it in a long time, but I like it. And this is how you would set it up. You draw like this little sideways L. On the outside of the L, you can't read that, you put the x value, which is 2, right here. And then you list all the coefficients, and you need to put a negative 3 here. I forgot to do that. So negative 3, 1, negative 12, and negative 5. And those are the coefficients. And you have to make sure you have covered all of them. Like if there was just 3, 2, and then there wasn't this term, I would have to put a 0 for that coefficient. So we'll get to that in the next problem. All right, here's what you do with synthetic substitution. All you do for the first one is you bring down the first coefficient, and you write that right there underneath. Then, this is where the new stuff begins. Then you do your x value times that, so 2 times negative 3, and you write it up here, negative 6. And then you add down, so this becomes negative 5 here. And then you take your x value and you multiply by that. 2 times negative 5 is negative 10, and you place that right here. And you add down, and you're going to get negative 22. 2 times negative 22 is negative 44. And you add down, and you get negative 49. Oh, wait a minute. Look at right here. We said when f of 2 for this function, when 2 went in, negative 49 came out. This is the same equation, the same function. When 2 went in, negative 49 came out. And so that's how you do synthetic substitution. Let's do this one now. All right, so on the outside of your bracket, you put the value of x, and you make your little sideways L. And you write your coefficients just a little bit up high so you have a row to fill in the numbers here. So I have 4, 3, 2, and notice there isn't an exponent of 1, so I'm going to have to compensate for that. So first of all, my first coefficient is 1. The coefficient for this term is 2. For this term is 3. I don't have an x term, so I have to say that the coefficient for that is 0. And then negative 7. So I'm going to write here, this is my x term coefficient. Okay? Now I'm ready to begin the synthetic substitution. So you just bring down the first number, place that there. Negative 2 times 1 is negative 2. 2 plus negative 2 is 0. Negative 2 times 0 is 0. 3 plus 0 is 3. Negative 2 times 3 is negative 6, and that goes here. Add down. Negative 2 times negative 6 is 12. Add down. Look at that. Would you look at that? So there we go. Again, synthetic substitution to evaluate this function when x is negative 2. Pretty nifty. All right, let's look at end behavior. This is something new. It's kind of cool, actually. You're just kind of looking at the graph, and you're saying, you're looking at the arrow part. So let's say this function is going to go this way. It's going to keep going because of that arrow. And you can see that the x values are getting more and more negative. So you would say as x approaches negative infinity, like a sideways 8, that's my x values. Therefore, my y values are also approaching negative infinity. Okay? Now we got to do the other end here, where the other arrow, the other end of the function is going. So here, the x values are getting bigger and bigger and bigger, so they're approaching positive infinity. And if you think about the y values, or the output of this function, the y values are also approaching positive infinity. Now, here's how you tell by looking at a graph what the degree of the polynomial function is. I kind of count this part right here. So here's 1, 2, 3. So I'm counting this part of the function right here. And there's 3 of those. So it's a degree of 3. And the leading coefficient is going to be positive because you kind of have to look at, think about a parabola. When a parabola is facing up, remember, it was a positive leading coefficient. When it faces down, it was a negative leading coefficient. So you kind of look at the end part here, and this is facing up. So it's going to be a leading coefficient of a positive. It's like a parabola, sort of. Okay? All right, now look here. You can already tell, based on what I just said, this part right here to the right is going down. That tells me that the leading coefficient is going to be negative. So let's identify here, as x is getting more and more negative on this end of the function, so it's going to be as x approaches negative infinity, my y values are getting more and more positive, so f of x is approaching positive infinity. Now you look at this end of the function, the end behavior. Here, x is approaching positive infinity. It's getting bigger and bigger and bigger. But f of x, my output, is approaching negative infinity. All right, the degree here, again, let's count the kind of the straight parts. There's 1, 2, 3. So it's a degree of 3. Or better yet, we would say odd. We could just say odd. We don't know exactly that it's 3, but if this is an odd number, then we're going to say odd. Let's just say odd. It's safer. It's safer that way. Okay. And let's talk about this end behavior. This one looks a little bit different than this. Okay, let's count. We have 1, 2, 3, 4. Since we have 4 of those, it's going to be an even degree of some sort. And let's talk about this end behavior here. As x gets more and more negative, so we're going to write it ourselves this time, as x approaches negative infinity, f of x approaches on this end positive infinity because the y values are getting bigger and bigger and bigger. All right, then on this end, as x approaches positive infinity, f of x also approaches positive infinity because the y values are getting bigger and bigger and bigger. Here, it's just like a parabola. It's facing up. So it's going to be a positive leading coefficient. All right? This is basically the same thing except it's facing down. So let's look at the degree here. We have 1, 2, 3, 4. So we're going to have an even degree of some sort. It's facing down, so it's going to be a negative leading coefficient. And let's describe our end behaviors. So this end first. As x approaches negative infinity, f of x approaches also negative infinity because the y values are getting smaller, the output going more and more negative. In this end here, x is approaching positive infinity because the x values are getting bigger and bigger and bigger. But f of x, the y, the output, is getting smaller and smaller and smaller, so it's going to be negative infinity. Alrighty, so that's describing end behavior. Okay, now let's graph here. I'm not going to spend too much time on this. All I really want you to do is notice that the degree is even. So it's going to be one of these kind of funky looking graphs, it should be. And leading coefficient is negative. Okay, so that means that it's going to be facing down. And all I want you to do is to put these on the calculator. And I already did put this on my calculator as y equals. And I'm going to go to the table and get some values here. So I want you to fill in these values. I just chose some values that kind of fit on my graph. Okay, this is going to be 1, 2, 3, and 4. And then I'm going to have this. After I look at my y values, I'm going to determine what my y-axis will be. So I'm going to go down to -1 so I can fill in my table here. Oh, I got to go the wrong way. Sorry. -1 is 0. 0 is 6. 1 is 8. 2 is 18. 3 is 24. And 4 is -10. So I know for my particular graph I need to go up at least to 24 on the y-axis. So I'm just going to go up by tens here, or by ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's 20. And then you just plot the points, and that's all you do. So, and this would be -1. -1, 0. 0, 6. Is about right there. 1, 8 is about right here. 2, 18 would be about right here. 3, 24 is going to be about right here. 4, -10 is going to be about down here. So if you carefully sketch that with end behaviors, kind of looks like that. So there you go. We're not going to do this one, but I do want you to notice that this is an odd degree, so it's going to look something like those, and it has a positive leading coefficient, which means that the right side end behavior is going to be going up. All right, and then you would just do the rest of that on your calculator. And that is that.